Good day, calculus students. We are going to be doing something called Taylor Polynomials. I'm going to use a visual to explain what a Taylor polynomial is before we look at all these equations on the screen. This is simply the graph of e to the x. A Taylor polynomial begins by picking an x-coordinate. Let's do x equals 0. I'm going to use this as an anchoring point for making higher and higher degreed polynomials that mimic the behavior of this exponential curve at that point. For example, a 0th degree polynomial is just a constant, and when you graph a constant, you get a horizontal line. If I was to say, hey, what horizontal line best mimics this graph at that point, the horizontal line that goes through that point is that horizontal line. If I were to say, okay, well, let's find a first degree polynomial that best matches this curve at the point 0, 1, well, a first degree polynomial is a line. And the best first degree polynomial, which is a diagonal line that mimics this curve, is going to be the tangent line. So here's an image of a tangent line to the curve. We can go higher degree. I can create a second degree polynomial. So I can create a parabola that best mimics this curve. The blue graph is that parabola. Now, some things that the parabola and the curve have in common at 0, 1. They share three things. They have the same y-coordinate when x is 0. They also have the same slope at 0, 1. But they also share the next derivative up at 0. They share the same concavity at 0, 1. If I do a third degree polynomial, the blue graph and the red graph share four things in common at 0, 1. Y-coordinate, slope, concavity. They also match a third derivative at 0, 1. A fourth degree polynomial matches up to 4 derivatives, etc. There's a fifth degree. And zoom back in. You can see at fifth degree, the polynomial and the exponential function are virtually indistinguishable. In fact, the higher degree of polynomial you get, the more accuracy away from the point of interest, in this case 0, 1. So Taylor polynomials are these polynomials that are designed to match in more and more derivatives with a function at a certain point. And you can move where that point is. Let's focus on when x is 1. Let me change my scale here slightly. And the point would be 1 comma e in this case, because the red graph is e to the x. If I were to say, hey, give me a 0th degree polynomial that best matches this non-polynomial, this red exponential curve, at the point 1e. And that would be the horizontal line y equals e. If I were to do a first degree, there's a tangent line at that point. A second degree, there's a parabola that's matching the curve at that point. Here's a cubic that's matching the curve at that point. A fourth degree and a fifth degree. We can go higher degrees. All right, the formula for finding a Taylor polynomial, you have to first specify where the Taylor polynomial will be anchored to the function. So that's this choice x equals a. You also have to decide what degree you want. Let's go with a general formula for the nth degree. But you make those two decisions and you have a function that you start with, and then the rest of this is all automatic on how to create the polynomial. We're going to use a capital T sub n to stand for Taylor polynomial of degree n. Let's look at this version here, and then we'll look at the summation version. Let's say this was a 3 here. Let's find a third degree polynomial. We actually create the polynomial from constant up. If that n was a 3, then all this part here would be gone. So let's just focus on third degree for now, and then we'll generalize it. So the very first term will always be a constant. That constant will always match the function when x is a. So in other words, you can find that constant by plugging a into the function. The next term is created by doing the derivative of the function and plugging a into that. So figure out the slope of the tangent line at that point, then multiply that by that term, and that makes sure that our linear graph is shifted appropriately to be centered at wherever a is at. The x squared term, you do the second derivative of the function, plug in a, get a number, and you're going to divide by 2 factorial, and then put this quadratic term right here. The reason why that factorial is there, it's designed so that when you do derivatives of the Taylor polynomial, that in the end you just get things that match the derivatives of the actual function f. I'm not going to go into the details of where this formula came from, but it's actually quite easy to construct. You're just trying to get the Taylor polynomial and the function f to match more and more derivatives. By the time you get to the third degree term, we do a third derivative of the function, we plug a into it, divide that by 3 factorial, and then multiply it by this x minus a cubed. We do all 4 of these terms, and we've created a third degree polynomial that's going to match the function f at the x-coordinate a. Now in general, if you want this to be n and not 3, you just keep this process up until you get to this final term here, where you have the nth derivative evaluated at a divided by n factorial times x minus a to the n. When you see what looks like a power, but it's in parentheses, that's indicating a derivative. This is the nth derivative. Now, since this is really just a sum, you realize you can just write this whole sum using summation notation, which is what's written up here. So here's our sum. Here's where the derivative, the factorial, and the power, they're always k. K starts at 0 and it goes up to n. So if you were to use this summation formula and actually start writing terms out, you would begin by plugging in 0 for all the k's. So this would be the 0th derivative evaluated at a divided by 0 factorial times an x minus a to the 0. That's 1. 0th derivative means you don't even need to write that. And that's 1, so these are all just gone. You really just get f of a when you plug in 0. And then when you plug in k equals 1, it'll just be this term. When you plug in k equals 2, it'll be this term. When you plug in k equals 3, it'll be this term, etc. And you keep this up until you plug in k equals n, and you get the last term. Let's put this to use now. In this one example, we're going to find a third degree Taylor polynomial for the function f of x equals 4 over x, and it's going to be centered at x equals 2. We're going to do a T3, so we're going to essentially use this formula, but stop right there. We've got to figure out the first 3 derivatives of the function evaluated at a, and then whatever numbers we get, we plug into those 4 locations. I'm going to make a table to do this. It's going to have k to keep track of what derivative we're on. It's going to have the kth derivative of that function, and then the last column will be the kth derivative of that function specifically at a. In this case, a is 2. All right, the first thing is the 0th derivative. This just means, hey, plug in the original function right here. No derivatives yet. It's going to be better to write that as 4 times x to the minus 1. So I can just do repeated derivatives by using the power rule. Now we're going to have to go until we get to this term right here, which means I need to know up to the 3rd derivative. So when k is 1, that just means find the first derivative. Don't worry about rewriting that because we want to keep doing derivatives. 2, that means do a 2nd derivative. And one more derivative here. And now we want to do is plug 2 into all of these. So we have 4 times 2 to the minus 1. Well, 2 to the minus 1 just means 1/2. So 4 times 1/2, we get just a 2 out of this. Plug 2 into the next expression. 2 to the minus 2 means 1 over 2 squared. That's 1/4 times a negative 4. We get negative 1 out of this. The next one, plug 2 into the second derivative. 2 to the minus 3 is 1/8, and 1/8 times 8 is 1. Now let's plug 2 into the last one. 2 to the minus 4 means 1/16, and negative 24 times 1/16, negative 3/2. So these are the values of the function and its first 3 derivatives evaluated at 2. These numbers I just found are going to go into these positions. All right, so we have t sub 3. This 2 right here goes into that position, so we just start with a 2. Next, we plug this negative 1 into this position right here. So this will be plus. I put a negative 1 in that position, and then it's times an x minus a. That a should be a 2, because that's what a is in this case. And I'm going to simplify that to just a minus sign. Next, I'm going to take the second derivative evaluated at 2, which is a 1. That's going to go into this position right here. So we have plus a 1, and that's going to be over a 2 factorial. And then we have this x minus a, and a is 2, so x minus 2 squared. So we have one more replacement to do. This negative 3/2 is going to go into this position, plus a negative 3/2. That needs to be divided by this 3 factorial still. And we multiply that by an x minus a is 2, and that's being cubed. And that's how we create a 3rd degree Taylor polynomial. Let's go to Desmos. Y equals 4 over x. Then we have specifically x equals 1 is where we're trying to get things to match. Now we're going to make T3. So I'm going to go capital T, put a 3 right after that. It makes it a subscript automatically of x equals. Maybe one thing we could do to this is simplify some of this first so I don't have to type in these fractions. T sub 3 of x equals 2 minus. Don't worry about distributing that, but I do want to simplify what that looks like. 2 factorial is just 2, so that's just that 1/2 there. And then this last one, this will be subtraction. 3 factorial is 6, right? So we're doing like a 3/2 divided by 6. That gives me 3/12, which is 1/4. So now I'm going to start typing in this polynomial. Oh, hello, I made a total mistake. We're not doing this at x equals 1, we're doing this at x equals 2. There we go. Here's where we're trying to get our polynomial to match. Okay, so if you stop at the constant, t3 of x equals only the 2, then you're going to get the 0th degree best approximation of this curve. The next term was minus an x minus 2 inside these parentheses. That makes the tangent line. That's the 1st degree Taylor polynomial. Plus 1/2 of x minus 2, and to square on that. Now we have a parabola approximating this 4 over x graph. And we're going to go one more term. All right, and so there's our actual T3. And at the point 2, 2, the red curve and the purple curve share 4 things in common. They have the same y-coordinate, they have the same slope of the tangent line, they have the same concavity, and they have the same 3rd derivative as well. And it winds up producing a graph that when you zoom in, you really can't tell the difference between the original and the approximating polynomial. Okay, that's our 3rd degree polynomial right here. Find the 4th degree Taylor polynomial centered at x equals 1 for the given function. So let's first create T4. And to do that, we're going to have to create this little table where we do multiple derivatives. Specifically, into the kth derivative, we're going to plug in 1. All right, the 0th derivative. That just means the original function. And I'm going to write it as x to a power. Then we want to do the first derivative. Power 1/2 drops down, the new power is negative 1/2. Second derivative, multiply 1/2 and negative 1/2, give me negative 1/4. Power drops by 1 to negative 3/2. Third derivative, negative 3/2 times negative 1/4, that gives me positive 3/8. And new power drops by 1 to negative 5/2. Do one more derivative, we get negative 15/16. The new power is negative 7/2. Now in this case, we're supposed to plug 1 into all of these x's. And when you plug 1 into x to the 1/2, you just get 1 back. In fact, all of these, 1 to a power is just 1. So when I plug 1 into all these x's, I'm just going to get the coefficients. Now let's construct the polynomial. Fourth degree Taylor polynomial will be equal to, it always just starts out with f of a. Now in this case, a is 1, plus. The next term is f prime of 1 times x minus 1, plus. The second derivative, evaluated at 1, over 2 factorial, or just a 2 if you want, times an x minus 1 squared, plus a third derivative of the function evaluated at 1 over a 3 factorial times x minus 1 cubed, plus. Now we want to do a fourth derivative. You could do this little Roman numeral 4, I see that happen sometimes too, but usually when you go to fourth derivative and higher, you switch over to this notation. So there's the fourth derivative evaluated at 1, divided by a 4 factorial, and then times an x minus 1 to the fourth. The next step is going to be replacing all of these f's. So f of 1 is just this first number. F prime of 1 is that second number in our list, etc. So we get, all right, I'm just going to do one more step where I simplify the coefficients. Now let's get this coefficient here fixed up. This negative will make this just subtractions, and 1/4 divided by 2 is 1/4 times a half. So at negative 1/8 goes here. 3/8 divided by 6, all right, that's 3/8, or 8 times 6 is what's going to happen. That will cancel, leaving a 2, so 1/16. And this last one will be subtraction, 15/16 divided by 24. And we're going to be multiplying by 1/24 essentially. A 3 cancels into there, leaving a 5. A 3 goes in there, leaving an 8. And I don't think anything else is going to simplify. So we're going to get a 5 up top, and we have to do an 8 times 16, so 128. And let's call this good. Let's not worry about distributing this 1/2 or foiling this and then distributing. Let's leave this in terms of powers of x minus 1. All right, let's go to the Desmos. T sub 4 of x equals, and we're going to start typing this in, 1 plus 1/2 of x minus 1 minus 1/8 of x minus 2 squared, minus 1, not minus 2. So now we're seeing a parabola. The black graph is a parabola that's mimicking the radical function at this point, plus 1/16 of x minus 1 cubed minus 5 1/28 of x minus 1 to the fourth. Okay, so there it is. I typed it all in. It looks good. You can tell visually that you're probably correct because when you're near this point and you zoom in, I mean, they should look identical. This is a good indication that you found the right polynomial. Now we're going to follow the instructions. Use the Taylor polynomial to predict the value of radical 1.2. Let's call this, instead of y, let's use function notation. I'm going to call this f of x. If I wanted to find out what the square root of 1.2 was, I would simply plug 1.2 into that function. Let me make a vertical line, x equals 1.2. If I were to say, hey, what's the square root of 1.2? That's like plugging 1.2 into that function f. We can also plug 1.2 into the Taylor polynomial. So I can say, okay, well, what's t sub 4 of, and plug 1.2 into that. And notice that when you plug 1.2 into the original function, you get one answer. When you plug 1.2 into the Taylor polynomial, you get a different answer, but that they're very similar. Now what's happening here is if I were to zoom in, the blue line is where the two curves are matching. The red line is offset, so it should be true that if I zoom in enough, it turns out that they're not the same. The red curve that you're seeing in the image now is the square root of x graph, and the black one is the Taylor polynomial. And if I click on the green vertical line at x equals 1.2, you're going to notice that these same two decimals, and how they're rounded here, they look identical. But if you look over on the left side, you can actually see that there is some discrepancy. And what's effectively happening is we're using the Taylor polynomial, or plugging 1.2 into that instead, and we're going to use that result as an approximation of the 1.2 you would get if you were to plug it into the square root of x. We can also do this by hand. Plug in t sub 4 of 1.2. It would look like 1 plus 1/2. Plug in a 1.2 in for this x, subtract 1, you get just 0.2, and 0.2 is 2/10 or 1/5. Minus 1/8. Plug in 1.2 for this x, subtract 1, that gives you 0.2, that's 1/5, and that's going to be squared. Plus 1/16 times, you're starting to see a pattern, this is just going to be 1/5 cubed. And then finally minus 5 1/28 times 1/5 to the fourth. And let's see what actual fraction we get. Desmos does this for us because this is a rational expression. Notice next to the t sub 4 of 1.2, there's the symbol, so you can convert your answer back and forth. So plugging in 1.2 into the polynomial gives us 17,527 over 16,000. And this fraction is an approximation of square root of 1.2. Okay, now why this was useful back in the day, without calculators, we did not have a way to say how big square root of 1.2 was, but this Taylor polynomial allows me to create a polynomial and plug 1.2 into that instead, and then I figured out this fraction by hand, and then I could have divided it and got a decimal, all of this by hand without using a calculator. Okay, let's do the fourth degree Taylor polynomial centered at 0 for the given function, tangent of x. A lot of the stuff I'll be able to copy and paste. Our new a is 0. Also in our formula here, all of these 1s need to be replaced by zeros. So this will be f of 0, f prime of 0, x minus 0, f double prime at 0, x minus 0 squared, x triple prime at 0, x minus 0 cubed, and then finally the fourth derivative at 0, x minus 0 to the fourth. Original function, tangent of x. First derivative of tangent is secant squared. I'm going to do an impromptu change of instructions here. Let's just go up to t3. Let's make that a third degree instead. And I'm also going to sense a need to perhaps extend my table, give myself some space to work here. The next derivative, okay, we have to think of this, right, secant squared is really this, and then do a generalized power rule, right? So the 2 drops down, the new power is 1 less, but the chain rule says now multiply by the derivative of the inside, which is going to be secant x tangent x. All right, so when all is said and done, the next derivative is, so you have a secant times a secant, so that's a secant squared, there's a 2 in front, and then a tangent. Let's do one more derivative. We've got to do a product rule next. My u times my v, and the derivative will be u prime v plus uv prime using product rule. So we're going to differentiate this part first. So 2 times 2 gives me a 4 in front. We have secant, power drops to a 1, but then chain rule times the secant tangent. So all of this is just my u prime. And then times v plus u times the derivative v. And the derivative tangent is secant squared. All right, so what does this wind up becoming? We get 4 secant squared tangent squared, and then plus 2 secant to the fourth. I need to add another column to this though, so I'm going to do some rearranging again of my work. And in this last column will be the kth derivative of the function evaluated specifically at 0. Okay, now we plug 0 into all these derivatives. So tangent of 0 is 0. Secant of 0 is 1, and then square that, stays 1. Tangent of 0 is 0. This 0 right here is just going to kill this whole thing and make it all 0. Tangent of 0, that's a 0. So that's going to make all that there 0. But secant of 0 is 1. Raise it to the fourth is still 1 times a 2. And let me crop off that term there. We decided to stick with the third degree, which means I also need to change that to the 3. So we have a third degree Taylor polynomial. Right, this entry right here goes into this spot. This entry here goes into that spot. This will go in right there. And then finally that will go in right there. So f of 0 is just 0. F prime of 0 was 1. F double prime of 0 was 0. And third derivative was 2. 0's gone. X minus 0 is just x times a 1. So we just get x in front of here. This whole term zeroes out because of that 0. And the final term, 2 over 3 factorial. 3 factorial is 6. 2 over 6, so this is just a third. And then we have an x cubed. And there's our third degree Taylor polynomial for this function. If I had said, hey, find t sub 1, you would have done these 2 terms. If I had said find t sub 2, you would have found these 3 terms. But because this one is 0, t sub 2 winds up being the same thing as t sub 1. Right? This will sometimes happen. It's not always the case that you get a different polynomial every time you try to do 1 degree more. T sub 3 of 0.5, which is 1/2, right? So plug 1/2 into both these x's, cube the 1/2, you get 1/8, times a third gives you 1/24, and add that to 12/24 gives us 13/24. So the claim is at 13/24, and that will be approximately equal to the tangent of 0.5.